I'm very happy to introduce where he's actually going to tell us about advances in perturbation theory, apparently from Heisenberg's office. So thank you for giving a talk, and please go ahead.
Well, thank you so much for the kind invitation. It's a pleasure to be back at Trinity, even if virtually only, and great to see some great friends and distinguished colleagues. The story I'm going to tell today is, I understand this is a broader audience, and so I hope to give an idea of the spirit of what's going on in scattering amplitudes, which of course you're quite familiar with at Dublin. But also some of the tools that we're using and some of the methods that I think we're trying to tackle, understanding some of the beauty and mathematical structure that we've seen in the form of scattering amplitudes. And so this talk is organized as, I'm going to start with some motivation and really just talk about the empirical data about observables in quantum field theory. What do they look like in broad classes of theories? Functionally, say, and try to address why perturbation theory is so hard. I'm sure most of you don't need to be convinced that it's hard. And then I want to talk about generalized unitarity and some of the new methods that we're using to try to really capture some of the intrinsic mathematical form of these amplitudes. So, but to set the stage, and just in case there's anybody in the audience who's a little less familiar with the physics, quantum field theory is just modern day force equals mass times acceleration. It's not a theory itself. You need to supply the F's and the M's. And it's really just the unification of relativity and quantum mechanics. Among the observables that people talk about, and what I'm going to focus on today, are scattering amplitudes, which encode the relative probabilities of all of the possible outcomes of any given experiment. You have some things coming in and some things going out. And scattering amplitude is this function of many variables that include of all the momenta and helicities and colors of the particles involved. And the two things that are resounding themes that I think set the stage for this whole story is that they are notoriously difficult to compute, often requiring supercomputer efforts. I'll give you a sense of that as this goes. And yet, every single time we've computed any observable in pretty much any quantum field theory you can think of, the prediction itself that's actually made for the actual experiment mocks us by its simplicity. Really begging the question, why was it so hard to calculate? And couldn't we have come up with a different strategy that made that more manifest as we went? And that is, I think, broadly speaking, the goal of the modern day amplitudes program, which is to make the simplicity less surprising. But it's always good to, Nima Arkani-Ahmed likes to say that this is a phenomenological subject where the data are the predictions made by quantum field theory. And it's a good idea just to step back and take a look at what some of the predictions look like. And can't start with any better example than the most famous prediction in quantum field theory and the most precisely tested prediction in all of science, which is the gyromagnetic ratio of the electron, which is not actually an amplitude, it's a ratio of two amplitudes, but fine. At leading order perturbation, this is a single Feynman diagram, and you get the number 2. This got Dirac his Nobel Prize. And at one loop, this is a calculation that we ask our students to do in a quantum field theory course. It's about a week of algebra, numerator algebra, spinors and gamma matrices. And at the end of the day, you get a Feynman integral. You have to integrate over the momenta of the internal particles. And as most students learn very quickly, Mathematica doesn't know how to do that integral. It's very hard. So you learn some tricks. And anyway, when all the dust settles, you find the number 1. And of course, 1 is obviously a very simple number, but it's hard to say. This is not really, this is not as rich as functionally, this is not rich at all. It's just a number that's being predicted for experiments. At 2 loops, this is something that took a decade to do. And it's only 7 Feynman diagrams, really not that hard. But if you imagine that it was a week of homework for one diagram at one loop, you can easily see why it could take 10 years. And if you were interested in the predictions made for experiments, you should be satisfied by that kind of representation. Very, very many decimal places. But I suspect that most people in this audience and would be much more satisfied by writing that instead of the decimal expansion, which is all you really need for the experiments, in this kind of beautiful mathematical form. And again, it's hard to say whether or not a number is simple, but you can see among here, you have the zeta of 3, the zeta function, which is the third polylogarithm evaluated at the number 1, pi squared, you get log 2. So you have numbers with certain kinds of structure. And it's kind of interesting from a number theoretic point of view. Why are there these numbers and not others? And why is there this kind of tower of different transcendental weights and not? When you go to higher loops, you have more diagrams, of course, and this was something that you never could have asked a student to have computed, and I don't think you would have ever done it before the era of supercomputers. First done by Kinoshita, and it was done numerically to slightly higher precision than Kinoshita had. At 3 loops, you find this kind of decimal expansion. And again, if you're an experimentalist, if you want to match the experiment, this is all you really need. But of course, some of the more interesting structure is exposed when we can write this, as Laporta did, rewrote this, to infinite precision. And among the things here, the zeta function, logarithms, rational numbers. And then there's this U31, which is related to the 4th polylogarithm evaluated a half and log 2s and things. But this is something that can be, Mathematica knows this and you can compute it to infinite precision. And clearly this is much more beautiful, I guess. But interestingly, and I hope some of this piques some of your interest, that beyond 3 loops, no analytic expression is known. And it's not for want of trying, and it's not from want of precision. This has been computed to tens of thousands of digits at 4 loops. The reason why no analytic expression is known is because some numbers appear which have no names. In particular, Clabiau periods appear, and I'll come back to that in a little bit. And so we can't write a pretty expression for this just because some of the numbers just don't have names and we don't know anything about their algebra. We don't know much about their algebra or how they work with each other. But this is something that, any precision can be had. It's worth comparing this to a similar kind of prediction in a possibly arguably nicer quantum field theory, like maximally supersymmetric Yang-Mills and the planar limit. A kind of close cousin of the G-2, or at least a similar kind of thing where we can compute to high precision, is the cusp anomalous dimension for 2-to-2 scattering. And this is something that has actually been computed famously using integrability. And what do you see? Actually, I should have made this alternating, but I guess you could imagine an imaginary coupling or something. So up to the alternating signs, what you see is that at every order of perturbation theory, this is a sum of zeta values, classical zeta values, so single, not multi-zeta values, single ones. And you'll notice that every single line has a fixed transcendental weight. It's for the even ones, we're talking about powers of pi, and et cetera. So you can see that it just explores this, and it's got integer coefficients. I mean, these are beautiful things, and they're extremely hard to compute from the Feynman expansion. And this idea, and in particular, this particular result in planar maximum supersymmetry led to this idea of maximum transcendentality, that maybe n equals 4 would be the nice theory in which all of the predictions would be classical polylogarithms and full weight, unlike G-2 that we just saw in QED, or pure Yang-Mills for that matter. One of the points of this talk I really want to raise is that the meaning of maximal transcendentality is very unclear. I do believe there's a sense in which that's true, or at least where I would bet on it, but not according to the definitions that were around when these ideas came about. But I'm more interested in functions of not just numbers. It's hard to say whether or not a number is simple, and it's hard to say that it's surprisingly simple, although I hope you will agree with me that these are simpler than G-2. And so, but what's really fueled this progress in scattering amplitudes has been the investigation of functions of many variables. Well, unfortunately, when you open up a textbook and you follow the rules, the Feynman rules, to make predictions for experiments, it's safe to say, I mean, I just believe it's true, that really all but the very most trivial predictions for experiments, those involving very few external states and often at the very lowest orders of perturbation, are either computationally completely intractable, or, I mean, in computational intractability is something that varies with time as computers get better. But if you just throw anything at it and just sum the Feynman expansion, even if you can do that, it's completely and theoretically inscrutable. And so it's very hard to say what, it's hard to make predictions, and it's very hard to see any kind of simplicity in it, which is a shame because scattering amplitudes are extremely important in many contexts, and particularly in collider physics. They occur this kind of event, which has two particles come in, two gluons, and it creates four jets, happens millions of times a second at the LHC. It's a very important background. And these kinds of predictions were literally viewed as computationally intractable, hopeless. And to prove my point, there was a paper in 1984 outlining the challenges, the theoretical challenges. There were plenty of experimental challenges, but the theoretical challenges to be overcome to deal with what was then being planned, the superconducting supercollider. And among the many challenges they mentioned, they pointed out the cross sections for elementary 2 to 4 processes had never been calculated, and that their complexity is such that they might not be evaluated in the foreseeable future. And then they asked the readers to maybe find estimates in certain restricted regions of phase space. Well, it's not hard to see why they viewed this as fundamentally intractable or deeply intractable. You just open up a textbook and you follow the Feynman rules, right? It's not so bad. At leading order of perturbation, this process would be generated by, would be encoded by 220 Feynman diagrams, each one of these diagrams being dozens and dozens of terms. And so we're talking about thousands and thousands of terms. There's no way you're ever going to do this on a pen and paper. And yet, because it was so experimentally important, and also probably because of this challenge of saying that it was impossible, two physicists at Fermilab put their backs into it, and through every theoretical trick, they introduced from modern perspective, they used it spuriously, but anyway, they introduced supersymmetry to relate it to something simpler. They used supercomputers. They thanked the supercomputer in the paper. And as soon as they got the answer, they rushed it to publication with a beautiful one-sentence abstract. The cross-section for 2 gluon to 4 gluon scattering is given in a form suitable for fast numerical calculations. What did it look like? The paper, not unlike many papers actually in this field, is just a formula. I mean, it's an 8-page formula with a page and a half of words around it. And I know you can't read this, but those are matrices of coefficients, and it's just at leading order, just the sum of the Feynman diagrams. But what really makes me love this paper is at the very end, after apologizing for not giving any details, they ended on this quixotically optimistic note. Furthermore, we hope to obtain a simple analytic form for the answer, making our result not only an experimentalist's, but also a theorist's delight. And I've asked them, and it's very hard to say why they put that sentence in that paper. They had some vague intuition that these things could collapse, that they could simplify them from some intuition about 2 to 2 and 2 to 3 that they had worked on. Well, anyway, within 6 months, they stumbled upon a guess that they checked numerically, matched that 8-page formula, that must have exceeded their wildest dreams. That process can be represented in this one simple formula in notation they didn't quite use, but that's okay. But what is way more exciting than having 8 pages go down to 1 line is that if you just stare at this for a few seconds, it's natural to conjecture that you could generalize this to not just 2 to 4, but 2 to any number whatsoever. And so they put it out as a conjecture, published in Physical Review letters. And another beautiful one-sentence abstract. And if you don't appreciate the magnitude of this simplification, just consider when 2 gluons create 50, the number of Feynman diagrams, even ignoring the number of terms, exceeds the number of atoms in the universe. And you can't help but think that maybe this the summing of the Feynman diagrams is somehow missing something fundamental. If all of these 10 to the 82 terms are all canceling each other out to give you something so beautiful, shouldn't you have been able to guess that? And I think largely speaking, going back to the goal of this whole program, is to make the simplicity of amplitudes manifest in the way that we compute them. Okay, but this is just leading order, and it's natural to wonder what happens at higher order. Well, a big insight uh, uh, that's going to form a lot of for the second part of the talk is that you can actually postpone the question of doing Feynman integrals and regulating and everything like that, and talk just about the sum of Feynman diagrams, and as an initial, progress. And at one loop, it was known, it's been known for quite a while that this particular process, at least in a theory with supersymmetry, is very simple. It's just a sum of little boxes. What about at higher loops? Well, as I'm going to come back to, it was known, it's been known since the 70s, that you could choose bases of integrands in which you could expand answers. And at two loops, this really becomes a fundamentally difficult problem. And it was first tackled by Christian Vergu in 2009, who chose a basis and solved all the cut conditions. And I'm going to show you, I'm going to have more to say about all that in a little bit. But his answer spanned a mere 12 pages, this formula. And you won't be surprised, within 6 months, we had guessed, again, just guessed, a much more compact formula that matched the right answer numerically. And within a few months of that, we got a little cocky and went to 3 loops. And I want to emphasize that these formulas, these 2 and 3 loop formulas to all multiplicity, were very much in the same spirit of the original Park-Taylor guess. We had some machinery in our back pocket to compute the right answer, and we knew that these numerically matched the right answer, but they were not derived. These formulas were not derived. And what has changed in the intervening years, and particularly in the last 2 or 3 years, is that this is now a science, it's not a guess. And we can write down similarly compact formulas for any observable in any quantum field theory. Okay, but I hope some of you are wondering, what about the functions that come out of this? These are Feynman integrands, so that's what these pictures represent. What happens when you integrate them? Well, if you want to get a prediction that's not just a number, it's actually kind of hard to do, and especially if you want something that's an actual observable, or even in a toy model quantum field theory, you have to define something that's UV and IR finite, some actual function. It turns out that the first non-trivial function of many variables that you can calculate that's hard to, that exposes anything interesting is actually this 2 to 4 process that Park and Taylor started with. And in the case of planar theories with maximum supersymmetry, and basically using the form very similar to what Christian Vergu wrote down in that 12-page formula, Del Duca, Dur, and Smirnov broke their backs and calculated everything, regulated everything, and found the finite observable that's called the remainder function. And in this heroic work in 2010, they introduced a ton of new techniques and ideas, followed by the answer in the appendix, which spanned a mere 18 pages. And of course, you can't read any of that, but these, if you could zoom in, you would see that it's G of something plus G of something plus G times G of blah. And these G's were, as they define in the paper, were contra polylogarithms. And there's a nice story to be told, but in the interest of time, I'm going to skip over it. But you will not be surprised that within 6 months, that 18-page formula collapsed to 1 line. And this is completely typical, not just in this amplitudes program, but really in quantum field theory in general. Every time somebody calculates something new, heroically by some means, they find that the answer itself mocks them by their simplicity. And we stare at it for a while and we figure out how it can be used. And this kind of simplicity was found using tools that were new to physicists and have, once we understood how to use them, they became industrialized. And indeed, the state of the art is now for this particular process, is now known to 7 loop, or actually it's known to 8 loop order, by mostly through the work of Dixon and his collaborators. And in this case, these are all polylogarithms of weight 2L, and there's a beautiful understanding about this class of functions. Okay. Now, I think if you were to just step back and if you were to poll experts, even quite recently, and ask them what kinds of functions come out of perturbation theory in a general quantum field theory, you would have gotten an answer probably similar to what I'm about to say. So, of course, you have the loop expansion, the perturbative expansion. And at tree level, there's just sums of Feynman diagrams. There's no integrals to do. And so you get a rational function at leading order. And at one loop, In 4 dimensions, you'd get weight 2 polylogs plus weight 1 polylog plus rational. And you can replace 2 with floor of d over 2 if you'd like to talk about general dimensions. But then you'd have this kind of an organization of pieces. And at 2 loops, you'd have weight 4 polylogs, etc. And at higher loops, you would just see these things. And this notion, oh, and the coefficients of amplitudes in these things were very special. And there's a whole side story, which I spoke about last time I spoke at Trinity. But the coefficients are very special, and I wish I had more time to talk about them. They're on-shell functions, they're gauge invariant. They aren't called leading singularities. They're not necessarily what people used to call leading singularities, but they are things that have no transcendental weight, and there's a beautiful story to tell about the coefficients. And I'm not going to have any time to talk about that. But planar maximum supersymmetry, so this notion of maximum transcendental in the case of polylogs is pretty clear that it's a weight blank polylogs 2L, and that somehow maybe n equals 4 would live in this top slice, which is certainly true for this 2 to 4 scattering that Dixon and his collaborators have computed to such high order. And unfortunately, and more recently, we've learned that this is not how things look. And part of the reason why I think if you had polled people, they would have gotten it wrong is because it is generally true that in any quantum field theory at 1 loop, you get polylogs. That is a completely general statement. But at higher loops, we've now found a lot of reasons to believe that this is not a big enough class of functions. And this understanding really took a while for everybody for it to really sink in. But I don't think it really needed to, because it's not hard to find counterexamples to these polylogarithm kind of conjecture or idea that people had. And the simplest class is something that happens in massive theories in 2 dimensions. And the simplest one is 2 loops. One of the first graphs you'd write down in 5-4 theory, in massive 5-4 theory. It's pretty easy to see that that is not a polylog. In fact, it is an elliptic logarithm. It's a finite thing in 2D. But if you keep adding loops, what you find is that there's always a log piece, and that's because every 1 loop integral in 2 dimensions is a log, but that the non-log logarithmic piece of it grows bigger and bigger. So at 3 loops, you get a K3 integral, and at 4 loops, you get Calabi-Yau threefold, in fact, and it keeps going. And of course, another name for K3, this manifold is Calabi-Yau twofold, and elliptic integral is a Calabi-Yau onefold. Interesting. But of course, this is in 2-dimensional massive theories. And you might wonder, why does it matter? Why does it matter to me or to our quantum field theories? Well, for one thing, they occur in our nice 4-dimensional quantum field theories, especially when you have masses sitting around. For example, this Calabi-Yau threefold contributes to electron G-2. It's what Laporta has spent a lot of time computing to tens of thousands of digits. He called it a double elliptic integral, I think. But the point is that it contributes. It is a contribution that you need to know to the gyromagnetic ratio of the electron. Okay, but maybe some of you, and I think people historically really tried to avoid this as much as they could. So maybe massless 5-4 theory, you're free of all this stuff. And in fact, there was even a conjecture by Kontsevich that in massless 5-4 theory that all of the renormalization constants and things that you would ever compute would always be polylogs of a very special class, multi-zeta values, what they were called. And the first exception to a vacuum graph, at least, was found at 8 loops by Brown and Schnetz in 2011. But what's interesting is that, so this is just a counter term kind of coefficient, and it is known to be a K3 period, but it's a bit of a shame that nobody was looking at amplitudes instead of just renormalization constants, because if they had looked at amplitudes, the counterexamples occur way sooner. So even in massless 5-4 theory, these corners that are wedges, you can just imagine as 2 massless legs if you'd like. And at 2 loops, you have this 10-point function for 5-4 theory, and that is an elliptic integral. But in fact, the chain continues. You get a Calabi-Yau twofold at 3 loops, Calabi-Yau threefold at 4 loops, And anyway, my collaborators and I started getting really good at finding counterexamples to things. In fact, there's an 8-point function for 5-4 theory, massless 5-4 theory, non-planar, that is a Calabi-Yau twofold. Anyway, so the non-polylogarithmic examples are just abound. In fact, you can easily find things at arbitrary loop order, fixed multiplicity, that are pieces that cannot be represented in terms of polylogs. And today, I think it's widely understood that outside of a small list of extremely limited, very simple classes of observables and very special quantum field theories, it's basically true to say that almost all observables and almost all QFTs are expected to be non-polylogarithmic. And these Calabi-Yaus, yes?
Can I ask a question? So for 2D, so would these exceptions be contain integrable quantum field theories or not? Or they also have this general behavior?
Well, so they occur as the coefficients in DIMREG in 4D2. So I'm just saying that they're finite in 2D is really the important thing. But these other examples, the train tracks and the tardigrades are all 4-dimensional examples that are finite also. So there's no divergences to care about. But it's worth bearing in mind, and I wish I had more to say about this. I really don't have as much to say, forgetting about even regardless of time. What's interesting is that at least in every instance that's understood very well, the Calabi-Yau itself is the simplest Calabi-Yau anybody would ever write down or talk about. It's a degree D+1 hypersurface in projective space of D dimensions, or some multi-cover thereof. And the kinematic data encode the moduli of these hypersurfaces, and they're often extremely singular. So although Calabi-Yaus have been very well studied by physicists for a very long time, most of the questions that physicists were interested in, especially motivated by string theory, they were interested in generic Calabi-Yaus. These are not generic, and not very interested in the periods of the actual integrals that we have to do. Okay. So it's worth stepping back. Why is perturbation theory so hard? Well, one reason is because Feynman diagrams are pretty terrible as integrals and as just functions. They're just terrible. And they're also explosive in number. They contain non-physical degrees of freedom. So all of the integrals that we read, that we get from a textbook, are just terrible things. Also, amplitudes, especially in theories like the standard model, aren't observable. You need to talk about ratios or cross sections. And that means that you need to regulate the amplitudes. And this regularization is often technically very difficult, and it deeply obscures any of the niceness that you might find. The other thing is that a lot of the most powerful techniques were built with motivation for colliders and very specific applications. And so they were really built, optimized for extremely low loop order, well, low loop or low multiplicities. And so the textbook methods that you can find aren't especially good for noticing simplicities or even trying to see that something pretty is going on. But then even if you understand, even if you can capture everything else, the fact is we don't really understand this Calabi-Yau geometry that's needed to describe these functions. And it's natural to ask, how could we possibly make it easier? And this is the subject of the second half of the talk, which I'm going to get to in just a moment here. But the basic idea is to use unitarity to not look at the Feynman expansion and instead focus your attention on the simplest integrals you can possibly do. And I'll justify why you can do that in a little bit here. But of course, what defines an integral as being easy changes with time. And as you get better new methods and new techniques, an integral that was easy using textbooks may not be easy today, and it's vice versa. And the other thing is to find integrals that integrate to nice functions that expose as much of the transcendental structure as possible without any of the crap that might go along with it. And in particular, search for pure integrals. And I wish I had more time to talk about this. I will a little bit later on, but for the sake of physicists, I'm going to say that a function is pure if there exists some sort of grading of functions by weight. Weight, I'm putting in, I didn't put it in quotes, but what I mean is anything. If you can have a space of functions such that the derivative of any of these functions results in a function which has been assigned a strictly lower weight. This means that the differential equations of these functions are nilpotent, that they project into decreasing weights. And whether or not weight is transcendental weight or polylogarithmic weight or whatever, as long as you can set up a system of differential equations like this, we say that there's a meaning to a function being pure. And it's very easy to find examples of functions that are not pure. Like take, for example, this set of Feynman propagators with 1 in the numerator. If you just put 1 in the numerator, what do you find? You get some kinematic thing that depends on some Mendel-Stams, but then you'll notice that it is the sum of 2 things with different functional coefficients. These trace pluses, it doesn't really matter what it is. The point is that because it is the sum of 2 different pieces with 2 different coefficients, any derivative you take of this thing is going to hit the outside first in the chain rule, and you can't even rescale it away. And so it's natural when you see this kind of integral that maybe you should look inside the parens and see the Li4s. Maybe this Feynman integral with 1 in the numerator should be written as the linear combination of pretty things just inside the parens, and that these coefficients are just the coefficients in that expansion. And that can be realized. Another thing is that avoid regularization whenever possible. So, for example, is it really necessary for us to expand observables in terms of divergent crap? Can you talk about observables directly in terms of integrands that do not need to be regulated? And the answer is sometimes. And the list of things that we're able to do this way is growing with time. But this is a big open area of research. Okay. So the key behind all of this is this, and actually one of the big seeds for progress in this field is generalized unitarity or unitarity-based strategies. And I'm going to give you a couple definitions and ideas for how this works and how it's being used to help expose some of these simplicities in a moment. So, but broadly speaking, it's a very simple idea. The Feynman integrand is some rational, or at least or algebraic, but usually it's rational differential form on the space of loop momenta. Well, rational differential forms span a vector space. I mean, rational functions with bounded degree span a vector space. And as such, you can just choose a basis of arbitrary rational functions. And you can write an amplitude in terms of that basis. Now, this idea really had its origins in making life easier at one loop. Where Passerino and Beltman noted that if you had an integral with more than d propagators and d dimensions, that you could decompose it as a sum of integrands with fewer propagators and d dimensions. And that meant that the number of integrals you'd ever have to do was bounded. You could collapse it. And that meant that you could tabulate the results of Feynman integration, which is the hardest thing, in just some appendix and look it up every time. And these coefficients, we'll talk about how to match those, are just matched by linear algebra. It's not very hard. And for any fixed quantum field theory, meaning space-time dimension, particle content, and loop order, I should say, the space of all amplitude integrands is finite dimensional. This is just a true statement. And so it can be a regulated space-time dimension as well. It doesn't really matter. The point is that at any loop order, there exists a finite sized basis in which every particle, particular amplitude in that theory can be represented. I mean, when I say any, I mean any multiplicity, any helicity group, any colors, anything, any other quantum labels you could talk about. So for example, in the standard model, there's some finite sized basis of Feynman integrands you can write down in which every single L loop process can be represented. This is very interesting. But I think that one of the lessons of unitarity is that it gives us permission to focus our attention on good integrals. Like, why waste our time with bad ones when we can actually just choose good ones? Every single Feynman integral, I don't even care if it's coming from a quantum field theory, every rational function of loop momenta is a potential basis element. And if you find a really good one, it's probably worth keeping in a basis. And this, it gives us permission to focus our attention on specific integrals, regardless of the particular quantum field theory in question, because you can always use it as a basis element. And so why not just try to look for the best, easiest integrals, the ones that expose the most structure, and use those. So the way that you actually find these coefficients has historically been done using generalized unitarity, which means that you match it on on-shell cuts. So the idea here is that if you have a basis of a certain size, you choose the same size, same number of cycles, a spanning set of unitarity cuts or generalized unitarity cuts. And this thing, it's called a spanning set if the period matrix is full rank. So you have some basis of integrands and you compute the coefficient, so these omegas are compact maximal dimension contour integrals, and you compute the period, which is loop independent, on every single integral. Okay. And by the way, what I'm saying right now has nothing to do with planarity, loop order, or anything. You just have a big basis, you pick a bunch of cycles, and you construct this matrix that's full rank. As soon as it's full rank, the coefficient is linear algebra. So the scattering amplitude evaluated on that compact contour is called the leading singularity. And this again, these things have beautiful structure and enjoyed infinite dimensional symmetries and all sorts of nice things that I wish I had more time to talk about. So you can compute that without doing the Feynman expansion. These are built in terms of trees where you're gluing things with on-shell particles into each other. Okay, but anyway, that's the point is I can compute these A's. Well, if you use the top line, you now consider this expansion. You just put in the period matrix there, and it tells you that that the jth coefficient is just A dotted into the inverse matrix of this period matrix here. Now, for reasons that I want to get into, I want to show you a little bit how this looks like and how this has historically been done. At one loop in 4 dimensions, you can write down a basis. There's also their numerators and whatever, but this for what I'm about to say, this is sufficient in cartoons. You have boxes, triangles, bubbles, and other things that integrate to 0 in dim-reg. So in 4 dimensions, what is the coefficient? What kind of contour should you choose to match field theory on? And the natural contours would be ones that cut 4 propagators. Those are maximal dimensional. So the coefficient of the boxes are these box pictures where these corners represent tree amplitudes and they're glued together in an on-shell way. It's called an on-shell function or on-shell diagram. Okay, but now what about the triangles? Similarly, I can compute the triangular cut in field theory. It's a product of 3 trees now. But is that the coefficient of that integrand? Well, no. And the reason is because the boxes have support on triangular cuts as well. And so the actual coefficient that people would have written down is actually the triangle minus all of the pollution from the boxes in your basis, if you want to match field theory. And similarly with the bubbles, the coefficient is not just the bubbles, but the bubble minus pollution from the triangles minus pollution from the boxes. And one of the things that my collaborators and I kind of stumbled upon is that this is a bad way of doing things. You picked a basis once and for all, and now you're solving for the coefficients in some crappy way. It's not very difficult linear algebra. It's a triangular system of cuts. So it's not that hard to do. But it turns out to be much more advantageous to actually redefine your boxes and triangles and bubbles this way, so that the top row on the left-hand side is now your new box integral, and its coefficient is exactly this corresponding leading singularity in field theory, and so on. And this idea of reshuffling the basis, so not just starting off with stupid Feynman integrals and solving for the cuts, but to actually diagonalize on a spanning set of cuts is called the program of prescriptive unitarity. It's a small little, conceptual change to unitarity. But the basic idea is very simple. You know that you start with some period matrices like this, and if you just take linear combinations of your stupid basis and, by combining them with the inverse of this period matrix, now the period matrix is the unit, is the identity, or the Kronecker delta function. And the coefficients in field theory are not some stupid linear algebra, but they're just the leading singularities in field theory. Now, this idea, I think, is extremely simple, but it has some very important practical implications. It turns out that these prescriptive integrals are much more likely to be pure, to satisfy nice differential equations, and that this really is a good strategy for finding good integrals. Okay. But I want to talk a little bit about bases in broad terms for a moment, and talk about how different quantum field theories, how to compare when we talk about unitarity in Feynman integrals. So there's a simple way in which quantum field theories can be partial ordered, which is how many Feynman integrals do you need to do at a certain order of perturbation to capture an amplitude? And part of this partial ordering is utterly obvious and trivial. So for example, the standard model requires a bigger basis than the standard model without the Higgs. Why? Because literally every Feynman diagram in the standard model without the Higgs occurs in the standard model. So obviously it's a superset. Standard model is a superset of, so as in these examples here, as we go from left to right, the Feynman rules are smaller, they involve fewer fields, there are just less Feynman diagrams. So obviously you need fewer Feynman integrals. And these are actually strict inclusions here. But what is surprising, and I think really interesting, is that the number of Feynman diagrams in your theory is not the right metric, because there is a very strict sense in which Yang-Mills is more complicated than n equals 2 super Yang-Mills, which is more complicated than n equals 4, and planar n equals 4 is clearly simpler, and fishnets, etc. But in this case, although going from Yang-Mills to super Yang-Mills, you are adding content, you are adding Feynman diagrams, you'd think that the complexity grows. It is true, and I don't have time to convince you of this, but it is true that the basis, the number of integrals you need to do, grows smaller. And this is the sense in which they are simpler quantum field theories. But I want to emphasize also that n equals 4 super Yang-Mills is not some stupid toy model, because these integrals are a subset of the integrals that you need for the standard model always. So every result that we do in n equals 4 is all of the hard work we need to do for understanding planar n equals 4 is some work that we absolutely have to do to capture pure Yang-Mills, non-supersymmetric Yang-Mills. Just because the basis is smaller, it's still a subspace. And so you need to do all of these things. And in this case, I mean, this kind of new partial ordering with supersymmetry, it reflects the better ultraviolet behavior of these theories. And it suggests that maybe you could carve up the basis to say that this subspace only is valid for, or, is the basis for n equals 4 is of some small little vector space of Feynman integrals that you need there. And then you can tag on some more and talk about the basis you would need for n equals 2. And then you can tag on some more and talk about the basis you need for the standard model. And you can carve up the space of Feynman integrands into these slices where better theories are matched in smaller slices. And this allows us, this can actually be done in general and doesn't need to reflect any of the physics really. It's really just a general statement that if I have a vector space of Feynman integrals big enough to represent amplitudes, if I divide it up into any subspaces by any means whatsoever, I can talk about the projection of the amplitude onto that subspace. And here I'm saying P because there's one way to do it would be to talk about power counting or something like that. But you can talk about the part of the standard model that has the same UV behavior as n equals 4. It is not all of the standard model, but it is a well-defined part, and it is expanded by the same basis that you'd need for n equals 4, say. And to first approximation, you might try to define some notion of power counting or how bad the UV behavior is. This turns out to be really subtle and very interesting for non-planar theories, and my collaborators and I proposed a way of defining these strata for non-planar bases, but it's not really perfect. So there's some interesting representation theory and graph theory to talk about dividing these bases in a more robust and useful way. But what I want to pose for the purpose of this colloquium, I'd like to propose just a bigger question that I think is much easier to understand, which is just, can we carve up the bases in ways that reflect the mathematical structure or the physical structure in which we care about in these predictions? So for example, when we saw the G-2 calculation, we saw things that were at the highest weight, and then we had rational pieces. Well, can I choose an integrand basis that is the outer sum of things with fixed weight? So I have these max weight pieces, and I have next to max weight pieces all the way down to rational, whatever weight means. Can I divide up the space this way? And then when I look at things in each of these classes, can I further subdivide it so that we have polylogs and we have elliptic logs and we have K3s? This notion of grading is called rigidity, or my collaborators and I coined that word. But this is a natural question as well. Can I come up with, two loop amplitudes in general are not polylogs, but can I find a maximal subspace of Feynman integrals, basis elements, that are pure polylogs when I integrate them? And can I separate them completely from the elliptic logs? Okay. Similarly, can I divide the basis into things which are finite and which are divergent? And this can actually be done in many ways. I mean, naively, you might say, can I do it by not just divergent, but the degree of divergence, whether it's 1 over epsilon or 1 over epsilon squared? Can I talk about UV and IR finite separately for the divergence? Can I talk about a UV divergent subbasis and an IR divergent basis? And I hope I'm giving you the idea that you really can carve up these spaces in these kinds of ways so that when you ask for a finite observable, say, it's fully spanned by the finite part of your integrand basis. And similarly, you can talk separately about the polylogarithmic pieces or the certain things of degrees of divergence, and you can see things canceling in finite observables directly. And by exploring theories without maximal supersymmetry at 1 loop and things with maximal supersymmetry at 2 loops in a couple forthcoming papers, we've been able to do this actually quite satisfactorily. At 1 loop, you can do this completely. At 2 loops, we've also seen how we can do this as long as you're willing to give up a few things like dual conformal invariance or something. This turns out to be possible. You can fully carve up the basis in this kind of a way, according to UV and IR structure separately, transcendental structure separately, and you can use this to calculate things much more efficiently. And interestingly, the bases that we're generating this way are very far from the ones that are generated by fire or something, the kinds of toolboxes that people have been using for integrand bases before. So I already mentioned this briefly, but one of the important lessons is that the best integrand bases, and this is an empirical statement, but the best integrals turn out to be the homological duals of cycles, things that satisfy that the integral over omega j is delta ij. Like I showed before, these prescriptive bases. And these kinds of ideas can really directly talk about finiteness by just choosing the cycles to expose, say, UV behavior in a certain basis, or to enclose IR divergent regions. And when you do that, the diagonalization procedure renders all of the integrals that are normalized on divergent cycles divergent, but the ones which are not normalized on divergent cycles vanish on those cycles. So it turns to makes things more finite. And so the basic idea is a mathematical one, and it's a very simple one, which is to think about Feynman integrals as representations of cohomology, and to not really spend much time thinking about them. Instead, spend your time thinking about the cycles and choose them to be the duals. And these cycles can be residues, elliptic periods, K3s, whatever. You can choose any maximal codimension cycles, maximal dimensional cycles, compact contour integrals you'd like to define these things. This trivializes the representation of amplitudes, as I mentioned, these prescriptive bases. But it also allows us to really isolate the subspaces in the basis that are infrared divergent, separately from those which are UV divergent, separately from those which are finite. And it results in integrands which were discovered long ago before we understood this logic, and were called magic integrals because they satisfy beautiful differential equations. They integrate to nice functions. And so choosing these maximal set of UV and IR divergence probing regions ensures that the basis does this nice split into things. And in ongoing work with a lot of my collaborators at Penn State, Cameron Langer, Kokimides, Nikhil, and Yatsi Zhang, and also some old collaborators like Yaroslav Trinka, we've been expanding our understanding of one loop amplitudes to beyond supersymmetric theories, beyond fixed integer dimensions, and really there's and understanding by kind of doing it how far we can push this carving up of integrand bases and to maximally expose the nice properties. And just like before, as soon as you make it easy to write down an amplitude, or once you've done the work on the basis side of things, it's very easy to represent amplitudes. And so with another forthcoming work, we're going to, that's being prepared right now, we've recently calculated, say, the first non-planar observable in maximal supersymmetry, the 6-point ratio function in very simple form, in a basis that exposes all of these infrared and UV structures. And there's a lot of interesting things that I wish I had more time to tell you about, like how you talk about double poles and weight drops and things like that, that we're learning by doing. And it's a very kind of exciting time to be thinking about these integrand bases. So I wanted to end with just kind of this broad picture of amplitudes. And I hope I've given you an idea of this spirit. But I think it really could be described as a virtuous cycle. Somebody computes something really hard to compute, either viewed as impossible very recently, or just beyond the current state of the art. And it really doesn't matter if you're talking about a toy model like maximal supersymmetry or fishnet theory, or you're talking about an observable in the standard model. It doesn't really matter. Somebody computes something really hard, and without fail, sometimes the same people, discover amazing cancellations. This happens again and again. And then you scratch your head and you spend, the bottom node is the hardest node on this cycle. You then spend sometimes years trying to understand why that simplicity happened, and see if you can reformulate the basic toolbox in a way that makes that manifest not so surprising. And once you do that, you can then exploit it into more powerful techniques and compute something that was completely unimaginable before you had these new methods. Take, for example, the 6-point remainder function, which was heroic and just 10 years ago at 2 loops and is now known at 8 loops. It is, it's incredible to see how far this can push this technology. And because we're not really talking about any particular quantum field theory, the applications abound. There are applications obviously to collider physics, but also to gravitational waves, to early universe cosmology, and a huge number of extremely interesting connections to pure mathematics, from function theory to number theory to algebraic geometry, combinatorics, graph theory, all of this that are not necessarily new connections to physics, but new applications. And it's been a ton of fun discovering mathematicians and mathematical knowledge that has these kinds of applications. So, and that's really all I wanted to tell you. So thank you very much. I realize I'm a couple minutes early, so anybody like to ask any questions, I'd be happy to take some questions.
Okay, thank you very much, Jake, for this very nice talk. Are there any questions?
Okay, question?
Hello?
Yep.
Sorry. So actually, it's actually, I wanted to maybe even follow up on the question that you asked, Marius. So you have this sunrise diagram, which is in two-dimensional massive theory. And as Marius was pointing out, if you had an integrable theory, like say sine Gordon, right? This is two-dimensional massive theory. Do you get these elliptic integrals? And also there we know the S matrix. Do you find particular simplicity there? And then also just to generalize a little bit, like this question about the basis, like, can you answer the same question for, say, these integrable theories? And do you find some sort of simplicity in these models?
Yeah, so I can't speak directly to us, I mean, to all theories in particular, but I know integrability isn't strong enough to protect you. These train track integrals, for example, arise in the integrable fishnet theory, and n equals 4 is widely thought to be integrable in the planar limit. So integrability certainly isn't strong enough to prevent them. The massive theories, these two-dimensional, the sunrise, which is unquestionably the best understood category of non-polylogarithmic Feynman integrals. Chuck Doran has a really authoritative analysis of these. You can show that they're elliptically fibered. There's beautiful recursion, mirror symmetry, all sorts of stuff is known. I don't know if those are relevant to all quantum field theories. In 2 dimensions, they're certainly not relevant to massless theories. I think I would bet a lot of money that a massless quantum field theory in 2 dimensions is polylogarithmic. But outside of that category, I can't think of a single category of any quantum field theory that is known to be non-polylogarithmic. And even the ones which I think everybody would bet on, like even 2 to 4 scattering that Lance has pushed so hard, there's a lingering doubt in my mind that that's the whole answer, because I know that they pollute these n equals 4 all over the place. And so it might be possible to define very limited observables that might be polylogarithmic, but I don't know how to do it. And I'm not sure of any quantum field theories where that's the case outside of massless theories in 2D. Yeah, but I think it's a great question. I don't know. If how much is this? How much is this has been looked at?
Thanks.
So I also have a question about way in the beginning when you discussed G-2. So you mentioned that the 3 loops you find the new class of numbers, which are not zetas and polylograms. So are you able sort of to define a number theory for these things by using your results with the integrals of Calabi-Yau's, or?
I mean, you can give them names and talk about them that way. I mean, that's how Laporta has proceeded. He has isolated as much of the structure. And so it's at 4 loops where you don't have names anymore. This thing is a polylog evaluated somewhere. But as far as I can tell, all of the conjectures that have been made along these lines have failed. So Laporta has, to infinite precision, all of these kinds of parts at 4 loops. What remains is that pesky sunrise diagram, which he's computed to tens of thousands of digits, and there's no name for it, but it is a period integral of a Calabi-Yau threefold. And these should be viewed as transcendental numbers with a certain kind of weight, but their algebra, their coproduct structure, all of these things are just completely undeveloped, I think is safe to say. And they're hard to compute. Mathematica certainly doesn't know how to compute a Calabi-Yau period. There are software packages that do, but they're experimental. So, glibly, you could write down analytically the 4 loop expression where there's one term in it that you just assign a name. It's this Feynman integral. But that's kind of cheating. I mean, it's not just because we have names of them. The fact that we have, the reason zeta 4 is a nice number in part, not just because it's been known forever and because it has a name, but because some of us know that zeta 4 is pi to the 4th over 90, and it's related to zeta values, and it satisfies algebras and coproduct structure. And we have a really robust understanding of how this number, theoretically, these numbers talk to each other. And I think as soon as you get to these Calabi-Yau periods, it's just a wild west. Nobody knows. I mean, and the things that we care about for amplitudes are functions, even the sunrise integrals. It depends, I guess, your predilections. If you view the masses as being defined in your quantum field theory, then the sunrises just give you numbers. But it's pretty natural to think of them as functions of the m's. And as you move around in the masses, you can see them degenerate. And so these are not just normal Calabi-Yau periods. They're very singular. They have very few non-shrunk, their period matrix is very low rank. And I think it's safe to say that this is poorly understood, even by people who know the most about Claviaus. Yeah. Which is a shame because we need them. Yeah.
Any further questions? So yeah, I have one more speculative sort of question is, so you still sort of go loop order by loop order, but do you already see some structure that would allow you to say something, say non-perturbatively, or something for finite coupling, for instance?
There's very few cases where that where I think we've seen enough perturbation theory to really, yeah. I mean, the only case I can think of where we actually understand enough loops to say something like that is an n equals 4, but that's actually convergent. So there's nothing non-perturbative there. There are no instantons to talk about in the planar limit. There are, G-2 are a few hundred orders away from being able to see any of the asymptotic structure, which is a shame because there's I would say it's widely believed by people who have not really mostly given it much thought. But I mean, I don't want to say that I'm skeptical about it. I'm in the category of people who believe it, that if you understood perturbation theory completely, that you would capture the non-perturbative structure implicitly by resummation. But that was actually an interesting conjecture with not a very large amount of evidence beyond dimensional quantum field theories. And in fact, some reason to be slightly skeptical. I mean, the basic question of whether or not the non-perturbative completion of Yang-Mills is unique. I think most people would say it probably is. If you know the perturbation, then there's a unique instanton sector. But there is very little evidence for that. It's very interesting. And I'm not sure, QCD can easily become non-perturbative at a lower loop level, but I don't know if there are any examples where we've actually calculated it high enough to start to answer some of those questions. But they're really interesting questions. Yeah. So maybe I should say I'm on time. I guess I gave 5 minutes for questions, so instead of ending early.
Actually, can I ask one more question?
Yes, please.
In the non-planar limit, is it possible so I presume maximal transcendentality goes away. Is that correct?
It's not believed to. So I'm sorry, it is widely expected that maximum supersymmetry is maximally transcendental, even in the non-planar limit.
Even in the non-planar theory?
Yeah.
Oh, okay.
We have some evidence for that, but it's pretty weak. So I would say, and we have very few observables. So it's been tested very weakly, I would say, but it's widely believed.
Okay. And yeah, I guess, I mean, do you know why? I mean, actually, sorry, is there any reason? I mean, I don't even know the reason in the planar limit, but is there any reason?
Yeah, I mean, people don't really know the reason in the planar limit either. I mean, yeah, that's a very good question. So what we have more evidence for is that non-planar maximum supersymmetry, just Yang-Mills here, supergravity is totally not in this line, appears to have extremely good ultraviolet behavior, even non-planar, to every loop order we can check. And so, I mean, but the evidence is kind of scant. A few years ago, we literally checked all multiplicity, a certain end of the KMHB amplitudes at 3 loops, and to check that they were free of poles at infinite loop momentum. And there, at 1 loop, that's at least pretty clear that if you have no support at infinite loop momentum, or let me say it another way, at the integrand level, the signal for transcendentality drop is when you have double poles. And it's really a sign that your theory should live in a lower number of dimensions. And so if you want to talk about the standard model, for example, it's actually much better, instead of saying that you have a 4-dimensional basis of integrams, it's much better to say that you have a part of it which is maximal weight in 4D, and then another part which is maximal weight in 2D, those are the logs, and then another part which is maximal weight in 0 dimensions, when those are the rational terms. And you can organize the basis that way. The fact that n equals 4 lives inside the maximal weight part of it is I don't know. I don't know how to justify it without computing it and checking that it's true. But I guess what I am saying is that in general you can stratify your bases by dimension, and that is a proxy for transcendentality. And so there is a well-defined maximal transcendental slice, I think.
Okay.
As long as by transcendentality, you're allowed to talk about K3s and everything. And n equals 4 appears to live in the best slice, whether it's planar or non-planar. But yeah, I don't have a better answer than that.
Okay, yeah, thanks. That's interesting.
Any further questions? Okay. If not, then let's thank Jake again. Thanks very much.
Thank you.
Nice and inspiring talk.
Good seeing you all.
Yeah, look forward to seeing you again in person sometime.
Yes, hopefully soon.
Yeah. Okay.
Yeah.
Thanks. Bye.
Bye. Thanks.